Our advancements in understanding nature have shaped our world for the past centuries. Numerous physicists contributed to the vast field of quantum physics. Today, we know that quantum physics is the operating system of nature. And so, to simulate nature's complex processes, we need a quantum computer. We use four main quantum effects for technological applications: energy quantization and tunneling since the middle of the last century are the basis for the first-generation quantum applications like lasers, photovoltaics, electron microscopes, MRI machines, transistors, and so all of microelectronics. Now, we are at the brink of utilizing two further effects in developing a whole new technology: quantum computers. In a classical computer, the basic computing units are little switches called transistors. Each of them is either open or closed, which represents a 0 or a 1 in the digital code. In a quantum computer, however, the basic units are the quantum bits called qubits. Several companies work on prototypes of this technology, like Google, IBM, Intel, and many others. This quantum computer from IBM uses a series of cooling methods to make its processor superconductive. The processor chip is located at the lowest point in this machine and operates at a temperature of -273 degrees Celsius, almost the lowest temperature physically possible and colder than in outer space. The low radiation noise environment is necessary to apply two further quantum effects which allow qubits to perform calculations. Like classical bits, qubits can have the state 0 or 1, but by radiating microwave signals on them, they are brought into so-called superposition, which is the first effect. A superposition state is a mixed state of both 0 and 1 at the same time that is unknown to us living in a classical world. After interactions with each other, the qubits retain some kind of link without any noticeable further connection between them, forming an integral state of all the qubits together. This second effect is called entanglement. By applying these effects for different qubit operations many times, the quantum algorithm is performed. On measuring the qubits, each of them turns into either 0 or 1 with some probability. This is the result of the algorithm. The whole process is repeated many thousand times to give a statistically relevant result. This only takes seconds. A classical computer would need decades or even centuries for the same outcome. To double the memory of a classical computer, you need to double the amount of transistors, but on a quantum computer, already a single qubit you add will double the memory. For now, these computers only exist as prototypes, and to be commercially useful, quantum algorithms still need substantial amount of research. But the envisioned solutions for very difficult calculation tasks could again revolutionize our world, like classical computers did before. We partnered with IBM and Google, who are actively developing prototypes, while Daimler is focusing on the areas of actual application. In the next years, we expect several promising applications. Material sciences, like the simulation of complex molecules. We could find new materials which improve on today's electric car batteries. Artificial intelligence. The training of advanced machine learning models could efficiently be done on a quantum computer center. And mobility solutions. We could create more intelligent navigation systems that would avoid traffic jams by assigning distributed routes to millions of participants. There are still major steps ahead to reach the goal of a fully functional device of this type. One of these milestones is called quantum supremacy. This is the moment when, for at least one theoretical problem, a quantum computer exceeds the calculating power of any existing classical computer, ringing in the beginning of a whole new chapter of technological advancement.